So we were talking about prime numbers. So we talked about this definition. The original definition was that a prime number is a natural number greater than 1 that has only itself and 1 as factors. So 2 is a prime number. We talked, at the end of the class, I think we were trying to figure out what the prime numbers were between 0 or 1 and 100 or 2 and 100. And we use that spreadsheet, and it has a special name. It's called the sieve of Eratosthenes, and basically you go through and filter out all the stuff that's obviously not a prime number, and what's left over are the prime numbers. You won't have to remember what the definition is, but you'll have to recognize if a number is a prime number. There's a second definition, which is a prime number is a natural number that has exactly 2 different natural number factors. And the reason that just clarifies that 1 is not a prime number, because prime 1 has really 1 factor, which is 1. And even if you said it had 2 factors, which were 1 times 1, they wouldn't be different. So 1 is not a prime number. But 2 is, because you have the factors of 1 and 2, which are different. So we did that in class. Now, part of this section talks about something that's called the fundamental theorem of arithmetic. Each part of math has some fundamental theorem. There's the fundamental theorem, the fundamental theorem of arithmetic says that every natural number can be expressed in one and only one way, as a product of prime numbers. This unique product of primes is called the prime factorization of a natural number. So that's what we're going to talk about next, is how do you come up with the prime factorization for any number. And the way you do it is you basically start with your number and you divide by the smallest prime number, which is 2, until you can't divide by 2 anymore. And then you go to the next larger prime number, which is 3, and you keep dividing by 3 until you can't divide anymore. And then you keep doing that until you end up with your last number is a prime number. And so the number itself is factored not into the factorization like we have done before, but it's factored into just prime numbers. Now there's a fundamental theorem of algebra, and the fundamental theorem of algebra talks about factors. So, for example, let me just put this on the get it unwrapped here. Okay. So you all have taken algebra, and you may not even remember if they talked about this. And you don't need to write anything down. I'm just going to tell you what it is. So the fundamental theorem of algebra has to do with factors. And I'm trying to remember what that actually has to, if you think about what you did in algebra, you ultimately ended up with things like algebra of just one variable. And when you do that, you can end up with a term that involves the variable and a term that involves a constant. And so you can think of that kind of like a factor. If you had a second order equation, like x squared plus 4x plus 3 equals 0, so it's a quadratic equation, you can factor that as x plus 3 and x plus 1 equals 0. And likewise, you can do that with higher order algebraic equations. You can factor them all. And I've not forgotten actually what it is, so I'm going to look it up. Let's look up what is the fundamental theorem of algebra. I can explain it, but I can't remember it right now. Fundamental theorem of algebra. Okay, so here it is. Let me copy that so you guys online can see what it is. Okay. Okay, so there's the fundamental theorem of algebra states that every non-constant single variable polynomial with complex coefficients has at least one complex root. Okay. Yeah, you don't need to memorize. This is just a little extra stuff that you don't need to know, but I'm just telling you because I think it's interesting. So, what does that mean relative to my comment here? Well, it says that every non-constant single variable polynomial, this is an example of a single variable polynomial with constant coefficients, which means this has a constant coefficient of 1, this has a constant coefficient of 4, constant coefficient of 3, that has at least one complex root. In this case, it has two roots. One root is x equals -3, and the other root is x is equal to -1. Those are the roots of the polynomial. And so in this case, I have one root. In this case, I have two roots. If I have a third order polynomial, I have 3 roots, and so forth. The order of your polynomial tells you how many roots you have. In this case, these are real roots, -1 and -3. If you had something like x squared plus 2x, plus, make sure I do this right here, say plus 7 equals 0. This has roots, but they're not real. They're actually imaginary roots. A complex number consists of a real part and an imaginary part. Okay. Anyway, the bottom line is, and I'm not going to get into complex numbers, but basically it has to do with roots of the polynomial. And then there's the fundamental theorem of calculus, which has to do with finding, when you deal with calculus, there's two important things you do. One is to find the slope of a line, and the other is to find the area underneath a curve. So here's a function, and if I wanted to find the area underneath the curve, so how many square units do I have below this curve, above the x-axis, and to the right of this line and to the left of that line? The fundamental theorem of calculus has to do with calculating this area. Anyway, there are these fundamental theorems that, what's that? Oh, I'm blue again. What are the, oh, that's because this came loose. Yeah, thank you. So anyway, there are fundamental theorems in math. Okay, so we're going to learn how to do prime factorization. And why do we learn prime factorization? Because when we deal with least common multiple, greatest common factor, it involves using the prime factorization of a number. So we're using this as a tool to help with something that is actually quite useful, which is finding the greatest common factor and least common multiple, which is in section 5. So there are 2 ways to do a factorization. I'm going to show you one. I tend to use one way just because it's more compact. Let's see, do we have a question here? Nope, just somebody came. So we'll use the factor tree first, which you may be used to. So we start with the number, and then you draw 2 branches off of the number. One number will be a prime number, and typically you use the smallest prime number, which is 2. So one branch is the prime number, one of the prime numbers. It's a factor of this number. And the result is this number divided by that prime number. So if you take 1440 and divide by 2, you get 720. And then you just keep this process continued until you get this number down to a prime number. So what we usually do again is we use 2, which is the smallest prime number, until we end up with a non-even number. So 720 is even, so we're going to factor it again with a 2. So you take 720 divided by 2 and you get 360. Is that even still? Yes, so we do it again. So we write down the next prime factorization, prime factor. 360 divided by 2 is 180. And again, I'm doing this in my head, but you can use your calculator when it comes down to it. Is this even? Yes, so I can keep going. So I divide 180 by 2, same prime number, I get 90. Then I ask, is that even still? Yes. So I still divide by 2, and 90 divided by 2 is 45. So here I am, I've gotten to the first case where it's not an even number anymore. So then I go to the next larger prime number, which is 3, and I ask, can I divide this number by 3? And the answer is yes. So 45 divided by 3 is 15. Again, I try 3 because and I'll continue to try the smallest prime number until I run out of options. So can you divide 15 by 3? The answer is yes. You can always use your calculator to check, see whether it works. The answer would be 5. And so I'm finished because my final number here finally comes down to a prime number. 5 is a prime number. So to do the prime factorization, you want to rewrite the original number as a product of prime numbers. And all you have to do is count how many times you have factored a particular prime number and use that as the exponent. So I've used 2 5 times. 1, 2, 3, 4, 5. So I get 2 to the 5th. Then I take my next prime number, which is 3, and I count how many times I've used that, which is 1 and 2, so that's my exponent. And then I finally multiply by 5. So that is what we call the prime factorization. Just doing the tree is not the prime factorization. The prime factorization is writing this out. Because what this is 2 times 2 times 2 times 2 times 2, 2 times 2 times 2 times 2 times 2, times 3 times 3, 3 times 3 times 5. So we use this shorthand notation with the exponent to represent the prime factorization. So again, we're going to be able to use that if we need to find the greatest common multiple, or greatest common factor, or least common multiple. So that's one way of doing it. I don't like that way because it takes up too much space. But so I use this method. It's the same basic process, but you write the number you're doing the prime factorization of, and you write the number you're dividing by each step over in this column. So it's all vertically instead of as a tree. So I say, 1440 divided by 2 is 720. Is that even? Yes, it is. So I divide by 2. 720 divided by 2 is 360. Is 360 divisible by 2? Yes, because it's even. I get 180. 180 divided, can I divide 180 by 2? Yes. The answer is 90. Is that even? Yes. So I can divide by 2 again. 90 divided by 2 is 45. Can I divide that by 2? No, because it's not even. Can I divide it by 3? Yes. 45 divided by 3 is 15. Can I divide 15 by 3? Yes. 15 divided by 3 is 5. And then I could write the prime factorization, which is, again, I just count the number of times that each number is used. So I've got 1, 2, 3, 4, 5. I've got 5 2s. I've got 2 3s. And I've got 1 5. So I get the same answer. You can do it either way. I'm going to do it this way from now on, just because, again, it takes up less space on my paper. Okay, so I've done that already. Okay, I'm going to do one more, and I'm going to ask you guys to do one. So, prime factorization of 300. Start with the smallest prime number, which is 2. Is the even number I start with even? Yes, so I can divide by 2. So 300 divided by 2 is 150. Is it even still? Yes, that means I can divide it by 2. I get 75. Is that even? No. So then I say, okay, can I divide it by 3? The answer is yes. 75 divided by 3 is 25. Can I still divide it by 3? No. So I go to the next prime number, which is 5. Can I divide 25 by 5? Yes. 25 divided by 5 is 5. That's a prime number, so I'm done. And so my prime factorization of 300 is going to be 2. And I've got 2 2's, so it's 2 squared. I've got 1 3, so I just put 3 down without the exponent. And then I have 5 twice. So that's the prime factorization. You can always check it out by multiplying these out. 2 times 2 times 3 times 5 times 5. And you find out it's 300. Now, besides being a math teacher, is there any way, how did I know 75? Why didn't I, you might say, well, why didn't you just divide that by 5? Because it's obviously divisible by 5, and that's true. But I tend to just go in order. I don't deviate. So then the question is, how do you know it's 75 is divisible by 3 without using your calculator? Well, we'll find out there are certain rules for figuring out whether numbers are divisible by other numbers. And the rule for 3's is that if you add the digits together, 7 plus 5, you get 12. And most 12 divided by 3, most people know, is 4, which is, so since 7 plus 5 is 12, which is divisible by 3, then 75 is divisible by 3. So that's why I knew it worked. If you take 2 plus 5, you get 7. 7 is not divisible by 3, hence 25 is not divisible by 3. The earlier ones, 300, 3 plus 0 plus 0 is 3. 3 is divisible by 3, so this is divisible by 3. 1 plus 5 plus 0 is 6, which is divisible by 3. So these were divisible by 3. I didn't do it at the particular time. So when you get down to a non-even number, all you have, and this number here is larger than you remember if it's divisible by or not. Like 51, you'd say, I can't remember whether 51 is divisible by 3, but 5 plus 1 is 6, which I do know is divisible by 3. So that's a rule that one of the rules that we'll learn here in a minute. Okay, so why don't you guys go ahead and do the prime factorization for 468. So for you guys online, if you can put your answer in there when you're done, and if you can, for example, the answer for the previous case would be 2, and you'll use a little caret thing, which is shift 6. So that would be 2 to the second, and then put a little x, 3 times 5 to the second power. So that's the format for writing the prime factorization. And when you get an answer, when somebody puts an answer in, if they can raise their hands so I can hear that they have an answer. So I don't know how long it's taking you guys. Again, you can use your calculator. Don't feel like you have to do it in your head. Let's see. You got one? waiting for somebody in line to ding in. Oh, there's somebody dinged in. Let's see what they did. Oh, okay. Somebody else did it. I think you've got the right answer. Your formatting is a little questionable, but so you take 468 and you divide by 2, which gives you 234. And that's still even, so I can divide by 2 again. So I divide by 2 and I get 167. No, I don't. That's not right. Let's try it again. It's 117. That looks more reasonable. So obviously you can't divide by 2 because it's odd. So we go to 3, and the rule says if you take this plus that, and you can divide the result by 3, it's divisible by 3. So you get 117 divided by 3 is, and I'm going to use my calculator just to show you that I'm not impervious to using calculators. So you get 39, and the question is 39 divisible by 3, which it is because 3 plus 9 is 12, which is divisible by 3. So I can divide that by 3, and I get 13. So you guys are right. So it says that 468 is equal to 2 squared times 3 squared times 13. So that's the prime factorization of that number. So here are the tests, and they're in your book. So dividing by 2 is easy because if it's even, you can divide by 2. Divide by 3, the sum of the digits is divisible by 3. So here's their example. It's a big number which we'd have no idea is divisible by 3. But if you add the digits, 8 plus 9 plus 7 plus 4 plus 3 plus 2, you get 33, which is divisible by 3. It's 11. And so I know this big number is divisible by 3. For 4, the last 2 digits form a number divisible by 4. So you look at the last 2 digits. In this case, this large number, the last 2 digits would be 32. So if this is divisible by 4, then the whole number is divisible by 4. And it makes sense because anything that's, if I took 7,693,400, anything that is 100, 0, 0, the last 2 digits, is divisible by 4. So if this whole thing is divisible by 4 and this is divisible by 4, the sum of the 2 is divisible by 4. See if you get, so let me explain that again. So if you took 7,693,400 plus 32, which is the number, this is divisible by 4. And so all you have to do is check to see whether this part is divisible by 4. So if you take 7,693,000, put it in your calculator, divide by 4, you're always going to get, when these last two digits is 0, it's always divisible by 4. So you just have to check the last 2 digits to make sure it's going to work. 5 is easy. Any number ending with a 0 or 5 is divisible by 5. 6, which is 2 times 3, it kind of makes sense. If you can divide the number by 2 and by 3, then you can divide it by 6. So the example they give in the book, 27,342, it's even, so it's divisible by 2. And if you add the digits together, 2 plus 7 is 9, plus 3 is 12, plus 4 is 16, plus 2 is 18. So the sum of these is 18, which is divisible by 3, and therefore it's divisible by 3. So since it's divisible by both 2 and 3, it's also divisible by 6. For 8, you have to take the last 3 digits and divide. If that's divisible by 8, then the whole thing is divisible by 8. That was not so easy. I mean, it's easier to divide 816 by 8 than it is the whole thing by 8. And you can't just say if it's divisible by 2 or 4, because if it's divisible by 2, it's also divisible by 4, so that doesn't give you any additional information. if the numbers added together are divisible by 9, then the whole thing is divisible by 9. So if I add these together, 4 plus 2 is 6, plus 8 is 14, plus 3 is 17, plus 17 plus 7 is 24, 24 plus 6 is 30. So these all, oh actually it's 36, I don't know what I did wrong there. Anyway, if you add all these up together, you get 36, and 36 is divisible by 9, and therefore the whole thing is divisible by 9. So it's kind of like the 3 rule, except it's just using 9 instead. And then finally, if the last digit is 0, it's divisible by 10. So those are the rules. We'll use them, I'll mention them as we go along. So they've got a couple of problems in the book where they give you a number and they ask you whether this number is divisible by all of the numbers up to 12. And I forgot to mention 12. So 12 is if they're, because 12 is 4 times 3, 3 times 4, it's kind of like 6, which was 2 times 3. So for a number to be divisible by 12, it has to be both divisible by 4 and divisible by 3. So we'd use the 4 rule and we'd use the 3 rule to see whether this is divisible by 12. And since 32 is divisible by 4, we know that the whole thing's divisible by 4. And if we add all these numbers together, the sum of these numbers is going to be divisible by 3. And therefore, because it's divisible by both 4 and 3, it's going to be divisible by 12. So let's look at the example here. So 321. So I'm going to write the numbers, and we're just going to mark them out if they're not divisible by these numbers using the rules. So is it divisible by 2? No, because it's not even. So that's not going to work. Is it divisible by 3? 3 plus 2 plus 1 is 6. So because these add up to a number that's divisible by 3, then it is divisible by 3. Now, once you've eliminated 2, you can eliminate every even number. So all of those get wiped out, because if it's not divisible by 2, it's not going to be divisible by any of these other numbers. And finally, it doesn't end in a 0 or a 5, and so that's not going to work either. So what is 321? Let's divide 321 by 3. We know it is divisible by 3, so 321 divided by 3 is 107. So either 107 is a prime number, or, yeah, I'm sure it is a prime number, unless you can divide it by 7, which I don't think you can. Yeah. So it turns out 107 is a prime number. Okay, let's look at this one right here, and I guess I'm going to have to scroll down a little bit. So again, we're going to write the numbers down and eliminate the ones we know are not going to work. 2, 3, 4, 5, 6, 8, 9, 10. I forgot 9. Is that an original question? Yeah, okay. It didn't work for 9 because, well, yeah, because 3 plus 2 plus 1, 3 plus 2 plus 1 does not equal a number which you can divide by 9. You get 6. 6 cannot be divided by 9 and be divisible, so that one also doesn't work. Okay, so let's look at this one. Is it divisible by 2? Yes, because it's even. Is it divisible by 3? Well, 3 plus 6 plus 3 plus 6 is 18. 18 is divisible by 3, so that's good too. To be divisible by 4, the last 2 digits have to be divisible by 4. So is 60 divisible by 4? The answer is yes, but you can check it on your calculator. 60 divided by 4 is equal to 15. So that one works. Is it divisible by 5? Yes, because the last number is 0. Is it divisible by 6? Yes, because it's divisible by 2 and 3. We've already determined that. Is it divisible by 8? Well, is 360 divisible? The last 3 digits Yes, so that works too. Is it divisible by 9? Well, we add the numbers together, which ended up being 18. And 18 is also divisible by 9. 18 divided by 9 is 2, so that one works. Is it divisible by 10? Yes, because the last number is 0. And is it divisible by 12? Yes, because it's divisible by 3 and 4 already, so we've already answered that question. So it's actually, that number is divisible by all those numbers. So again, 2 if it's even. 3 if the sum of the digits add up to a number that's divisible by 3. 4 if the last 2 digits are divisible by 4. 5 if the last number is 0 or 5. 6 if it's divisible by 2 and 3. 8 if the last 3 digits are divisible by 8. 9 if the sum is divisible by 9. 10 if the last digit's 0. And 12 if it's divisible by 3 and 4. So those are the rules that we have. Why did we leave out 7 and 11? Because there's no easy rule for that, okay? So if we end up having to try 7, we're just going to have to do it longhand or use our calculator. But typically that doesn't happen until we don't get to 7 when we're doing prime factorization unless we've gone through 2s, 3s, and 5s. And a lot of times, by the time you get to that point, there's not a whole lot. The number's not very big anyway. The rules turn out to be as complicated as just trying it by hand. So there's really no shortcut that allows you to use that. Okay, so there's the homework for section 1. Basically, factoring numbers and doing the prime factorization of numbers. Do you have to memorize prime numbers? No. Do you need to know what the prime numbers are up to about 20? Probably. So you will have to memorize some prime numbers, but those are the ones that, before 20, which is not that many. You can just write them on a piece of paper. What are the prime numbers? 2, 3, 5, 7, 11, 13, 17, 19. So those are the prime numbers less than 20. That's the only prime numbers that you'll need to know. So I don't actually assign any homework. I'm going to go through and we're just going to talk about the material. It's kind of an interest more than anything else. So the question is, a lot of people have asked the question, is there a number large enough that do you get to a number where every number above that is not a prime number? Because you think if the number is large enough, there's got to be some number smaller that you can divide by. If you have 10 billion digits, there's got to be some number that you can divide that by. Well, it's not true. There's always any number, you can always find a larger prime number. So possibly. So anyway, there are an infinite number of prime numbers. And even back in the Greek times, they proved that this was true. That there was always one prime number larger than the one that the largest one you figured out at the time. And what you do is you prove by contradiction. So you use an example to prove how you get the next larger prime number. So let's just assume that we've only figured out that 13 is the largest prime number. So how would we prove that there's a larger prime number than 13? And if we can prove that, you can always come up with a prime number larger than the last smaller number, then you can So what we do is you create a prime number by multiplying all previous prime numbers together, and then you add 1. And by adding 1 to this, you can prove that that number is a prime number. So let's just see if that works or not. So in the case of 13, what you would do is you would take all previous prime numbers before 13, or up to 13. So the previous prime numbers would be 2 times 2, 3, 5, 7, 11, and 13. So what it's saying is I can create a prime number by taking 2 times 3 times 5 times 7 times 11 times 13, and I add 1 to that. So 2 times 3 times 5 times 7 times 11 times 13 is 30,030. And if I add 1 to that, I get 30,031. And that's got to be a prime number, because I know that it's not divisible by any of these numbers here. And by adding 1, if I added 2, then I'd get a even number, which would be a prime. All prime numbers above 2 have to be odd numbers. So if I added 2, I wouldn't have a prime number. By adding 1, I have a prime number. I mean, if you did the prime factorization of this number, you get 2 times 3 times 5 times 7 times 11 times 13. So that's the way Euclid proved that you can always have larger prime numbers by taking any number that's a prime number and taking all the prime numbers less than that, multiplying together and adding 1, and that's going to give you a prime number. And you can do that no matter what the highest prime number you think there is. So there are an infinite number of prime numbers. So of course, mathematicians, I'm an engineer, so I can say this about mathematicians. Mathematicians just try to think of things that are interesting math-wise. So they would say, what's the largest prime number that we have verified is actually a prime number? Or how do you come up with larger and larger prime numbers? Isn't there just a formula for that? There's always a formula for everything, and there are formulas. So these are in your book. Again, we're not going to use them. It's just to show. So there's this thing called Mersenne primes, and the numbers are first, if you choose n to calculate this number, where n is either a composite number or a prime number. Remember, a composite number is a number that's not a prime number. So that would be 4, 6, 8. If you calculate this number but using n as one of those composite numbers, the resulting number is also composite. And if n is prime, then the number you result in may be either a prime or a composite. But if you use a composite number here for the exponent, it's definitely going to be composite. But because if you use n as a prime number, most of the time you do get prime numbers, except at certain values. So this turns out it works for numbers up to n equals 10, but it doesn't work for n equals 11. So let's put this on one page and think about what they're saying here. Let's just calculate the corresponding number for different values of n. So what I'm going to do is I'm going to make a table up, which is going to be n is one column, n sub n, and then I'm going to make a comment about it. So let's try n equals 1. So what you get is you get 2 to the first power minus 1. Actually, we shouldn't start at 1. Let's start at least 2. So we'll start at 2. So you get 2 to the second power minus 1, which is equal to 3. and that's prime. That is that prime? Yeah. So this is prime, and the resulting number that I get using the formula is prime. Let's try 3. So you take 2 to the third power minus 1, which is 8 minus 1, which is 7, and that's prime. So it's working so far. If this number is prime, then the resulting number is prime. This is a composite number. So if I take 2 to the fourth power minus 1, that's 16 minus 1, which is 15. This is composite. 15 is composite because it's not prime. It's 3 times 5 is 15. So that works. So it said when n is composite, which it is, the resulting number is composite. Okay, next one's a prime number. So we take 2 to the fifth power minus 1, which is 32 minus 1, which is 31, which is prime. So it's working again. This is prime. The answer is prime. If I do 6, I'll get 2 to the sixth power minus 1, which is 64 minus 1, which is 63. You can divide 63 by 3, so this is composite. So again, the rules prove true. If n is composite, which this is composite, it's not prime, then the result. Now 7, so you get 2 to the seventh minus 1, which is 128, minus 1, which is 127. Turns out that is prime, is a prime number. And you can keep doing that, and what it says is it works up till n equals 10, but if you try n equals 11, you'll get 2047. 2 to the 11th power is 2048, and you subtract 1, you get 2047. So 11 is a prime number, so you would think the resulting answer would be prime, but it doesn't work. It actually is not a prime number. So what we've seen is, for most of the cases, this formula does give me a prime number when n is a prime number, but it doesn't always work that way. Because how do I know this is not a prime number? What can you divide 2047 by? Well, you can't divide it by 3 because these add up to 13. You can't divide that by 3. So I'm not sure what you can divide it by, but apparently you can divide it by something. Okay. Caitlin's going on. Divided by, well, yeah, but that's a prime number. So anybody want to, let's just try something here. 2047 divided by 11, that didn't work. 2047 divided by 13, that didn't work. 2047 divided by 7, no. 7, 11, 13, 2047 divided by, what's the next prime number? 17, no. 2047 divided by 19, nope. Divided by 23. Oh, there we go. So it turns out that 2047 is 23 times 89. Okay, so that was interesting. So these prime numbers that you get by using that formula, the largest Mersenne prime verified as of 2010 was it was the 42 million M with n equal to 42,643,801. So if you take 2 to this power and subtract 1, it's a prime number. And if you go on Wikipedia, you'll find out the most recent Mersenne prime, which is bigger than this number. So it's constantly, I don't know if somebody needs a thesis to write or something like that, or just some funding, or they're just interested. But every once in a while you'll look up on Wikipedia and somebody will come up with the next larger Mersenne prime. Okay, so this, as of when I did this notes, which is a year ago, it was 2 to the 42,112,609th power. So let's see if they've changed it. We'll see if they've updated it or not. So if you go to Wikipedia and you search for what is it called? I can't forget. Spell it. MER, SEN prime. So the latest number, and if you guys are online, just wait a second. Right there, as of January, it's to the, there, that's the number, 74,207,000. Yeah. So it's another 30 million higher. So every year, if you go there, you'll find out that somebody's come up with a higher number. And then you have these different, as you go through the time period, you know, this is not something people have been thinking about just recently. They've been doing this for a long time. This guy in 1630 had this formula, which was 2 to the 2 to the n power plus 1. And it turns out that that works for 1, 2, 3, and 4, but not for 5. That wasn't a very successful result. This Euler guy, 1732, he came up with a formula, n squared minus n plus 41, and that works up until n equals 40, but it fails at 41. And this guy in 1879 came up with this formula, which works up till n equals 80, but doesn't, it fail, well, actually works until you get n equals 80. So that's it. That's all I'm saying about it. Now, what's the, is there any practical use of getting really big prime numbers? And the answer is yes, and it has to do, and I don't understand how it works, but it has to do with computer encryption. Exactly how it works, I don't understand. I haven't spent the time to understand it, but it is, actually there is a reason for doing this besides just the academic knowledge of what is the largest prime number. But the thing you should remember is, if you only remember one thing from this chapter, is that there's always a larger prime, there's an infinite number of prime numbers. Okay, next section. No homework assignment from that section. Nope. Okay, selected topics from number theory. This is also, there's no homework assigned to this either. So, and this is actually, I don't think it has any practical value at all. So it's more, it's kind of like, you know, looking at your phone number and seeing that the numbers add up to something weird. You're like, oh, that's cool. But besides that, besides being cool, there's not a whole lot that I can see that's it's important. Okay, somebody keeps binging. Scroll up. Oh, what is it? Oh, look at Jesse's. Okay, question. Okay, there we go. Jesse has a question. Oh, okay, what is the question, Jesse? Jesse has a question. I'm trying, Jesse. It's okay. Divide by 1. Okay. Where's your question? Is it way up here? Did I miss it? Jesse has a question. Oh, can you do problem 54? Oh, okay. Yes. It's 5-4. We haven't even got to 5-4 yet. I can't do it yet. I haven't taught it. Yeah, you gotta wait, Jesse. Well, Jesse's, yeah, she's ahead of the game. Because it's on, it's a spreadsheet, has a list of all the homework. She's just ahead. So when I get to that section, I'll explain it to you. Pardon me? Yeah. It's there's a spreadsheet that tells you what the homework is for each section. So you can do it. You can go ahead if you want to. Yeah. Jessie works full time, so she tries to fit it in where it's, so she might not have time, and you know, her kid might be sick in a week. You never know. So you. Okay, so this just basically talks about some interesting types of numbers. So there's things called perfect numbers, and a perfect number is such that the divisors or the factors less than that number add up to be equal to the number itself. So what does that mean? Let me just give you an example. So let me just pick, here's a number 30. If I list the factors for 30, So to do the factorization of 30, I know that 1 and 30 have to be factors. Then I try the next larger number, which is 2, and I ask, can I divide 30 by 2, which I can. So 15 is also a factor. 30 divided by 2 is 15. Then I go to 3. Can I divide 30 by 3? The answer is yes. So both 3 and 10 are factors. Can I divide 30 by 4? No. By 5? Yes. What's the answer? 6. So these are my factors. So if I add all the factors for 30 together, I will get a number. So 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 5 is 11, 11 plus 6 is 17, 27, 27 plus 15 is 42. Okay, so 30 does not equal 42. I did all that right. So 30 is not a perfect number. So what is an example of a perfect number? Well, 6 is a perfect number, because if I factor 6, I'll get 1 and 6, and I'll get 2 and 3. And if I add all the numbers up except the last number, 1 plus 2 plus 3 is 6. So the sum of the factors less than 6, proper divisors, which are these numbers, add up to 6. So 6 is a perfect number. It turns out there's one perfect number per decade. So there's one perfect number that has 2 digits, one perfect number that has 3 digits, and so forth. So what are those? 28 is a perfect number. Again, if I factor 28, I will get the following. So I think it's that. So 1 and 28, 2 and 14, and 4 and 7. So if I add 1 plus 2 plus 4 plus 7 plus 14, 44, you get 3, 3 plus 4 is 7, 7 plus 7 is 14, 14 plus 14 equals 28, and therefore the sum of all these add up to that. So that's the perfect number for the 2 digits. The next two are 496 and 8,128. So if you factored these and added all the numbers up except the factor of the number itself, they would add up to the number. Those are perfect numbers. So it's just kind of cool that, I guess there's 2 things that are cool. One is that it actually happens, and secondly, it turns out there's only one per decade. So if there's one that's a 5-digit perfect number, and you really, you can't really predict which ones are going to work and which ones aren't going to work. So the nth perfect number contains exactly n digits. So the first perfect number is 6. It has 1 digit. The second perfect number is 28. It has 2 digits. The third perfect number has 3 digits, and so forth and so on. So that's what that's saying. And the even perfect numbers end in the digits 6 and 8. So you'll notice this ends in 6, this ends in 8, this ends in 6, this ends in 8, so the next number will end in 6, and the one after that will end in 8, and it just alternates like that. It says if 2 to the n minus 1 is prime, then 2 to the n minus 1 times 2 to the n minus 1 is perfect. So what is that? Let's see if I can figure that one out, what that means. I'm trying to think of one. Well, let's pick a number n and see what happens. So I'm going to pick n equals 3. So if you get 2 to the third minus 1, that's 8 minus 1, which is 7, which is prime. Then 2 to the n minus 1 times 2 to the n minus 1, we get 2 squared is 4 times 2 cubed, which is 8 minus 1, 4 times 8 minus 1, which is 7, equals 28. So that worked. So for n equals 3, this number was prime, and therefore the number in the second formula is a perfect number. I don't know if, the next perfect number, which was 496, I'm not sure what value of n you need for that to happen. Okay, so that's perfect numbers, and you have something called deficient and abundant numbers, and you do the same thing, and if the sum of those numbers is less than the number itself, then it's called a deficient number, and if you add the numbers up and the sum of those digits is less than the original number, then it's called an abundant number. So for example, back here where I tried 30, these added up to 42. And since 42 is greater than the number, that's called, 30 is an abundant number, because when you add the numbers up, they're greater than the number itself. So that's some weird names. Okay. And then you got friendly numbers. So friendly numbers are if the sum of the proper divisors of A is B and the sum of the proper divisors of B is A. So what the heck does that mean? Well, let's look at an example of what a friendly number is. So 284 and 220 are friendly because if I factor 284, I get these 6 numbers. I don't include that, and if I add 1 plus 2 plus 4 plus 71 plus 142, I get 220. And if I do the same thing for 220, I factor 220 and add all these numbers up except 220, I get 284. So it's kind of a weird occurrence. This 284 would be deficient because the sum is less than, the sum of these numbers is less than 284, whereas 220 would be abundant because the sum of all these numbers except 220 is more than 220. So this is deficient, this is abundant, and these two numbers are friendly numbers because of that fact. Again, there's no practical reason, This was actually determined by the Pythagoreans, the same people that determined the Pythagorean theorem. The next pair of friendly numbers was found in 1636 by the same guy that came up with this prime number formula. So the next two friendly numbers are 17,296 and 18,416. I'll leave that up to you as an exercise if you're interested. We're not going to prove it. It turned out they missed, this Fermat guy, he missed, there's two other friendly numbers, 1184 and 1210. So if I factor this, add the numbers together, it'll equal 1210, and if I factor this and add the numbers together except for 1210, it'll equal 1184. And currently they figured out there are 11 million pairs of friendly numbers. So it's like prime, this probably has no practical use, but it's, again, some challenge for somebody. Why do people do puzzles? What else we got here? I'm trying to remember all this stuff again. We've got 3 little things, so let's finish it up. And then we'll move on to section 4 so I can answer Jesse's question. Every even number greater than 2 can be written as the sum of 2 prime numbers. So here's an example. 8, which is even, is 5 plus 3. 10, which is an even number, is 5 plus 5. So let's just look at a couple of examples of where that's true. So 12 can be the sum of 2 prime numbers, 5 and 7. 14 is the sum of 2 prime numbers. 16 is the sum of, just says the sum of 2 prime numbers. So what numbers together added 5 plus 11? Okay, so these are 2 prime numbers that add to 16. 18 would be 11 plus 7. Okay, these are 2 prime. So 20 would be 7 plus 13. So every even number can be written as the sum of two prime numbers. 22 would be 17 plus 5, or 5 plus 17. So it's kind of an interesting mind game here to try to figure out what two prime numbers added together result in an even number. And it says it can't be proved, but they have never found a case where it can't be done. Let's see. So this is kind of answer your question about how close together are they. Twin primes are primes that are separated by two units. So an example would be 3 and 5. Those are twins because they're separated by 2. Or what's another one? I think 11 and 13. Those are twins. It says there are infinitely many twin primes. So no matter how big a number you get, you can always find instances where there are two prime numbers that are only separated by 2 units. Now, probably all the other ones, they generally get spread out more, but you never get to too large a number where you don't at least get twin primes happening. I think it's just an interesting thing. I don't think there's anything. Yeah. So it's really here's more examples of where the primes are separated by plus or minus 1. And then the last thing, it says that for any natural number greater than 3, there are no triples that satisfy the equation a to the n plus b to the n equals c to the n. So we talked about Pythagorean triples. 3 squared plus 4 squared equals 5 squared. So that works for a lot of values of n. Or for n equals 2, there's a lot of choices for Pythagorean triples. If n is greater than 3, there are no numbers that satisfy that. So any number cubed plus another number cubed can't equal the third number cubed. It only works for squares. So you might think, oh, I can do that if I can say that, let me add a page. You might think, okay, if 3 squared plus 4 squared equals 5 squared, oh, that works out, that works for 2, so there must be some number like 3 cubed plus 5 cubed equals something cubed, x cubed. Well, it turns out that it's saying that there are no whole numbers where this works when you go to the third power or to the fourth power or to the fifth power. Only this Pythagorean situation only works when the exponent is 2. And it was proved. This guy lived in 16-something hundred, but he couldn't prove it. So there was always this challenge for mathematicians. Can you prove that the Fermat's last theorem was true or not true? They never found anything that violated it, but it wasn't proven until the 1990s. Somebody actually, and I think there might have been some prize. If you can solve this or prove this, you win $1 million or something like that. It probably wasn't that much, but okay. So that's it. We're going to move on to section 4 next time. No homework from that section either.